Hi, everyone. My name is Alan Yang, and today I'll be talking about some work with Mina and Grayscow in the Nav Lab at Stanford University. In this work, we show how several versions of the spreading code design problem for GNSS can be posed as mixed integer convex optimization problems. That is, convex optimization problems that have some additional integer valued constraints on the variables. This formulation of the problem opens the door to new optimization methods, which we find can outperform state-of-the-art approaches. We first briefly illustrate the spreading code design problem using GPS as an example. In GPS, each satellite sends its location and the time the signal was sent, and the receiver processes the information to figure out which signals came from which satellite and when the signals were transmitted. For simplicity, here we're just going to draw 4 of the satellites. The challenge is that the satellites share the same band in the spectrum, that is, the same communication channel. In GPS, a code division multiple access approach is used to allow the receiver to identify the signals sent from each satellite. At a high level, each satellite modulates its transmission with a unique binary code, which is known to the receiver. The incoming signal seen by the receiver has the transmissions from the different satellites added together. To extract the message transmitted by satellite 1, the receiver correlates a signal with the local copy of satellite 1's binary spreading code. The receiver can then look at the timing of the zero-shift autocorrelation peak to process satellite 1's signal. If the cross-correlation between satellite 1's code and the other satellite's codes is small, then we receive minimal interference from the other satellites when processing satellite 1 signal, for instance, with satellite 2 here. This is the main idea behind code division multiple access. So this motivates possible design criteria for GPS codes. First, we want low autocorrelation side lobes at shifts other than 0, essentially so that we can correctly identify the signal phase and get the timing right. And we also want the codes to have low cross correlations with each other so that there is minimal interference. In general, we have M spreading codes with unique codes x1 through xm. Each code is binary valued with ±1 entries, and each has length n. We define the cross correlation of 2 codes at shift k as the inner product between the first code and a shifted version of the second code. From here on out, we're going to use Cij sub k to denote the cross correlation between codes I and j at shift k, based on this definition. And finally, the autocorrelation of a code is just the cross correlation of that code with itself. For now, let's pretend that the auto and cross correlations are linear functions of variables. Later, we will see that we can express them as linear functions when we add additional auxiliary variables, which we will refer to as z. We might also have some convex constraints. That is, variables are restricted to be in some convex set C, and we will minimize a convex function f of the auto and cross correlations, binary variables, and auxiliary variables. We refer to a problem of this form as a mixed integer convex optimization problem. This is because we have a mix of continuous auxiliary variables and integer valued binary variables. And if we relax or remove the binary constraints, then we are left with a convex optimization problem. Later, we will discuss solution methods for mixed integer problems, which can exploit a convex structure. But first, we will see some example design criteria in the literature which fits into this framework. So the first example is the mean of squares objective, which is simply the average of all auto and cross correlation values at each shift. Here, the number of terms in the summation is on the order of n times m squared, specifically n times m autocorrelation terms plus n times m choose 2 cross-correlation terms. One issue with this objective is that, as we will see later, it can lead to solutions where the autocorrelations are significantly larger on average than the cross-correlation, since there are more cross-correlation terms in the summation. To combat this, we could instead minimize the maximum between the mean sum of squared autocorrelations and the mean sum of squared cross-correlations. And we will call this objective the balanced mean of squares. Other options include minimizing the maximum correlation magnitude or the mean of higher powers. And both of these are convex in C. We can also allow convex constraints on variables, as mentioned earlier. So one common example is the balance constraint, which requires that the number of plus and minus 1 entries in the codes are roughly the same. And this can help keep the DC level of the signal low. We can easily implement balance constraints using a set of linear inequality constraints. A more complicated example is the autocorrelation side lobe zero property. This requires that the shift 1 autocorrelations are minimal, which corresponds to 0 in the even length case and usually -1 in the odd length case. This constraint was imposed when designing the spreading codes for the Galileo constellation. And we can implement this using linear equality constraints on the entries of C. So as mentioned earlier, if the auto and cross correlation C can be written as linear functions of the variables, then we have a mixed integer convex optimization problem. So we will do this as follows. First, we will use the fact that for any two binary variables A and B, Z equals the product of A and B if and only if Z satisfies the 4 linear inequality constraints shown on the right. Essentially, the constraints ensure that for each of the 4 possible combinations of A and B, Z takes on the value of the product. We can use this fact to write each cross-correlation value, which is a sum of products of binary variables, as a sum of auxiliary variable Z subject to some additional convex constraints. So this establishes that the co-design problems that we looked at previously can be expressed as mixed integer convex optimization problems. So despite the convex structure of the objective, the problem is still non-convex due to the binary constraints. In general, there are 2 types of approaches for solving mixed integer convex optimization problems. First, we have global optimization methods. They can provably find the global solution, but tend to be fairly slow. For example, brute force search is a global optimization method. Later, we will discuss branch and bound, which is also a search method, but it can, in some cases, be significantly faster than the brute force approach. In contrast, local optimization methods are fast, but may not be able to find the global solution and cannot prove optimality even if it does. One example is to repeatedly loop through each binary variable and see if flipping its sign improves the objective value. So one global optimization method is branch and bound. It can be, in some cases, faster than brute force search. The basic idea is that in each step, we partition the feasible set into convex sets and find lower bounds on the objective value in each of the sets using a convex relaxation. That is, we relax or remove any non-convex binary constraints and then solve the relaxed problem to get a lower bound on the objective. If our current solution matches the lower bound, then we quit since we have found the global solution. Otherwise, we can refine the partition and repeat using the lower bounds to prune sets that cannot do better than our current solution. Unfortunately, branch and bound has exponential worst case complexity, and its performance depends on how efficiently the lower bounds can be computed and used to prune down the search space. In practice, we can use branch and bound to find optimal codes, but only for very small problem instances. However, we find that it can be an effective method for solving partial minimization problems. That is, we optimize codes only over a subset of the binary variables, with the others held fixed to the previous values. Since partial minimization preserves convexity, the partial minimization problems are also mixed integer convex problems. This suggests a local optimization method that incorporates a global method like branch and bound. So now we get into block coordinate descent. So in this approach, we repeatedly solve a partial minimization problem over a randomly selected subset of the binary variables. And here we can use branch and bound to solve the partial minimization block updates. The idea is that we can make the subset sizes relatively large, such that branch and bound can effectively do the block updates, but brute force search is impractical. In our experiments, we take the subset sizes to be 15. A nice property is that since the block updates are solved exactly, the objective function is guaranteed to be non-increasing between iterations. So we consider a problem of optimizing a set of 31 codes, each of length 1023. And this corresponds to the GPS codes. If we use block coordinate descent to minimize the balanced mean of squares objective mentioned before, where this is the maximum between the mean squared autocorrelation and mean squared cross correlation, we compare our approach against the gold codes, which are used by current GPS and a recently proposed natural evolution strategy. We find that block coordinate descent can find a better solution than the gold codes after around 50 or so iterations, and a better solution than the natural evolution strategy after around 300. As we can see, the objective value is strictly decreasing, so we can stop the iteration once a satisfactory solution has been found. We can also compare histograms of the correlation magnitudes for codes designed using block coordinate descent on the top to minimize the mean of squares objective, and on the bottom, the balanced version of that objective. When minimizing the mean of squares, the algorithm is able to find codes with very low cross correlations, but at the expense of somewhat larger autocorrelation values. On the other hand, minimizing the balanced objective, we see that we can achieve a somewhat better trade-off. This may or may not be desirable depending on the needs of the particular GNSS application, but illustrates how we can adjust the objective to achieve desired goals. And of course, other design criteria and constraints may be considered instead of the ones we have here. In conclusion, we showed how the spreading code design problem may be formulated as a mixed integer convex optimization problem. We believe that the convex structure can be leveraged to design better search algorithms and, as a result, better spreading codes. We demonstrated one possible method based on a combination of block coordinate descent with branch and bound. And in the future, we may have search algorithms can be used to find better spreading codes with any convex design criteria without needing to design a specialized solver for each of those criteria. And that's all. Thank you.